So, previous session we were saying that if you have an LBA, and so it's a Turing machine, and it has Q states, different states, and the length of your finite tape is n, so you have space for only n symbols, and the little g is the number of different symbols that you can have in your tape alphabet. Okay, in other words, capital sigma. So the size of capital gamma, capital gamma. The size of gamma is little g, right? Then there's a maximum number of different configurations that you can have, and that maximum number is this: qn g to the n. Is that sort of obvious? See, you've got q different states. You're trying to find the maximum number of configurations. Well, what is a configuration? Well, it's those three things, right? It's the particular state that you're in at a given moment, at a given step in the computation. So you have q of those, q possibilities there, right? Second thing is the position of the head. Well, there are only n squares in your finite tape, so the head could be at any one of those n different positions. So q times n, for those two possibilities. They're independent of each other, so you just multiply them. Okay. And then the third thing you need to specify a configuration is the contents of the tape. Well, if it's n squares long and you have little g different symbols from your tape alphabet that you could put into each of those squares, well, you can fill one square g in little g different ways, okay? And they're all independent. All those squares, you can fill them independently of each other. So you can fill the second square also in g ways. So that means you've got g squared ways. It's just combinatorics, right? So you've got g squared ways of filling the first two squares, and you can fill the third square also in g different ways. So the number of ways of filling the first three squares will be g by g by g, so g cubed, and so on for all n squares. So the possible number of different strings you can have of length n will be g to the n. G to the n. Okay? So you multiply all those three numbers, q different states, n different head positions, and g to the n different strings, and that product of the three, that will be the maximum number of different configurations you can have. Okay? And that's what Lem 5.8 says. This is what the lemma says. There are this many distinct configurations of m on a tape of length little n. Okay. Now the proof, well, I've sort of done it in words anyway. Okay. Well, here this is sort of more commentary leading in, but just a reminder of what a configuration is, right? It's sort of like a snapshot, like a frozen frame in a movie, where each frame would correspond to one step in a computation by a Turing machine. And so you go from one configuration to the next with the next step, and so on. Okay, and the configuration, those three things I mentioned, the state of the machine, position of the head, and the contents of the tape. Q states, length of the tape is n, okay, so the head can be in one of n positions, and you've done all that. There are g to the n possible strings of symbols that can be on the tape. The tape is of length n squares. The product of all these three is that by that by that, okay? And that's the total number of different configurations that your LBA can have, okay? End of proof. Okay. Now, the whole point of talking about that lemma is, it's a preliminary proof. It's a result that we will then use in a bigger proof, theorem. And here's the theorem. So 5.9, chapter 5, the ninth thing. You may remember me saying, perhaps surprisingly, I'm not sure. Depends what your intuition told you. But this language here is actually decidable. Different from ATM. You've had TM down here. ATM, we know, is undecidable. But in this case, A suffix LBA is decidable. And maybe that's fairly intuitive because of the nature of this type of machine. It's a constrained Turing machine. And you're probably guessing now we're going to use the constraint, this number in fact, and we will, from the lemma to help us prove this, that it's actually decidable. And what does that actually mean? Remember, a language is decidable if there's a Turing machine. Now, what kind of a Turing machine? This kind or the ordinary kind? The ordinary kind. In other words, a Turing machine with an infinite tape, okay, with infinite memory. So to say that this language is decidable means there is an ordinary Turing machine with infinite tape that decides the language. Okay? And what does that mean? A bit of revision, done this many times. It means that all the members of the language are accepted by that Turing machine, infinite tape Turing machine, ordinary Turing machine. And any other string is rejected. So, in other words, that Turing machine, that infinite tape Turing machine, ordinary Turing machine, is a decider. It decides. Okay? So it says accept or reject for every string. It makes a decision in every case, for every string. Right, well, how do you go about proving this? Well, the proof's getting quite long now, as we get more and more into the book. The proof idea, let alone the proof idea is a square, at least. Okay, so half a session. Now, as usual, when you're talking about the proof idea, usually there's a core idea, the essential idea that the whole proof is based on. So in this case, what is it? Well, we're going to simulate this thing using an ordinary Turing machine, an infinite tape Turing machine. Okay? So that's this essential idea. So a bit of a reminder, this language, how's it defined? So go back to the previous session. I can read it out to you. You can't see it, but this language is, it consists of elements which are angular brackets M, W, so the ordered pair, where M is an LBA, right? And W is just an ordinary string that goes into the LBA. Okay. Now, so this M and W, they are the two things in your element of this language. Okay. So we will use an ordinary Turing machine to simulate M. Now M, remember, is an LBA. So we're going to simulate what this LBA, called M, does when the string W goes into it, right? So we're going to get, in other words, we're going to get an ordinary Turing machine to simulate an LBA. That's the guts of the idea, right? Okay, now, so imagine the Turing machine, the simulation is going ahead. So if your LBA halts, we'll have the simulation also halt. In other words, if your LBA accepts, we'll then have the simulation accept. And if your LBA rejects, we'll have the simulation reject. So that's fine. Okay? Because after all, we're trying to have our simulating Turing machine, our ordinary Turing machine, infinite tape Turing machine, be a decider. Okay? So we want it to accept and reject. But there's a problem, of course. Turing machines can do three things. They can accept, reject, or loop. Okay? So what about looping? What happens if this LBA that we're simulating with a normal Turing machine, what happens if this LBA loops